Hello everyone. Forgive me because there's no light for right now in my home, right? So now I'm using camera flash. Okay, I hope you can see my notes very clearly. Okay, so this portion what I'm going to teach now is one of the most important portion. It's one of the most important topics in first module in information theory and coding, and that is marginal, conditional and joint entropies. Okay, this is a sure question which could come in the exam, and it is extremely important for each and every one of you to understand the concept, not just the equation, but also to understand what is the meaning of each and every concept and each and every equation. Okay, it's very important. And before moving on to this, before coming into this derivation, okay, I hope you all know what is entropy, right? We have learned what is entropy. What is entropy? It is the entropy of a source is defined as sigma k is equal to 1 to q pk log 1 by pk, right? This is called as the entropy of the source, or the average information of the source, average amount of information of the source, right? Where pk represents the probability of a single event or of a single message. And how many messages are there? There are q messages, right? So each and every, if you find the information of each and every message and multiply it with its probability, with its corresponding probability, and then add it, you will get the entropy, right? So one more thing about this entropy is that this entropy can be defined if you have a source. In the first place, you should have a source, and that source should have q messages, right? And that is not the only condition. Another condition is that if you add the probability of each and every message, if you add the probability of each and every source, which means if you add p1 plus p2 plus p3 up to pq, if you add the probability of each and every message of which you're transmitting, you should get 1, or sigma k is equal to 1 to q pk must be equal to 1. If this equation is satisfied, then only you can define the entropy of that source, right? So any source or any entity or any body, if or any, what do you say, a receiver or any kind of information or a set of events which satisfies this condition, in which the probability, the possible probabilities of all its outcomes is equal to 1, then only you can define the entropy. If this equation is not satisfied, then you cannot apply the entropy equation to that source. You need to understand this before moving on into my topic. So now we know what is entropy, right? Entropy is the average amount of information. And why does we know this is information? Log of 1 by pk is the information. And how do I find the average of this information? By simply multiplying this with each and every probability. By multiplying the information of every message with its corresponding probability and then adding it up. That's how I find the entropy, right? So you need to understand this before moving on into the entropy, different types of entropies. Okay, so in order to see the different types of entropies, what I do first is that I consider a very simple communication network. All right, so we know that a simple communication network consists only of a transmitter, a channel and a receiver. Okay, so here I'm going to name my transmitter as X and my receiver as Y. Okay, letters are very important. Always remember the letters which represents the corresponding concept. Okay, so we consider a simple communication network comprising of a transmitter X and a receiver Y. Okay, with the channel as the medium, right? Now this is very important. Let small letter x1, x2, x3 up to xm. Remember that the name of my transmitter is capital letter X and the name of the receiver is capital letter Y. Okay, so let small letter, okay, x1, x2, x3 up to xm be the symbols or messages transmitted by the source transmitter X, right? And let y1, y2, y3 up to yn be the symbols or messages received by the receiver y. Okay. See here, one thing you should understand is not only it's a small letters, these are all these messages represents these symbols represents the messages transmitted by the transmitter, and these symbols represents the messages received by the receiver. Okay, so here you should understand. So what is M? M is the number of transmitted symbols, and what is N? N is the number of received symbols. Okay, usually not usually I'm trying to generalize the communication system, because not all communication systems have the same transmitted symbols and received symbols, right? Most of the, or in order to generalize the communication system, most of the communication system has different transmitted symbols and different received symbols. That is why the two letters are different. Okay, so in other words, X, capital letter X, is a set of x1, x2, x3 up to xm, and Y is a set of y1, y2, y3 up to yn. Okay, now I'm going to assume that let P of x1, P of x2, P of x3 up to P of xm be the probabilities of transmitting x1, x2, x3 up to xm respectively. That means P of x1 is the probability of transmitting x1, P of x2 is the probability of transmitting x2, P of x3 is the probability of transmitting x3, and so forth. Likewise, let P of y1, P of y2, P of y3 up to P of yn be the probabilities of receiving y1, y2, y3 up to yn respectively. That means P of y1 is the probability of receiving y1, P of y2 is the probability of receiving y2, P of y3 is the probability of receiving y3, and so forth. Okay, then the probability of transmitter, the overall probability of transmitter P of x, okay, is nothing but it is expressed as P of x is equal to a set of, this curly bracket represents set, right? It's a set of P of x1, P of x2, P of x3 up to P of xm. All right, and also if we add all the probabilities of this transmitted symbols, right, if we add all the probabilities, we should get 1, because the probability of x1 plus the probability of x2, the probability of transmitting x1 plus the probability of transmitting x2 plus the probability of transmitting x3, which means that probability that x1 is transmitted, right, or the probability of x2 transmitted plus the probability of x3 transmitted plus the probability of xm transmitted. So which means that if we add the probabilities of all the transmitted symbols, which means that any one of them will be transmitted, right? So therefore it is equal to 1. Or in other words, sigma k is equal to 1 to m, P of xk is equal to 1, right? So this is my first equation. That is, if I add the probabilities of all the transmitted symbols, I will get equal to 1. Now, since I am able to satisfy this equation, then I can define my h of x. Right? I can define my h of x. So this is P of x. So therefore, I can define my h of x. Similarly, the probability of receiver P of y is expressed as P of y is equal to set of P of y1, P of y2, P of y3 up to P of yn. And likewise, if I add the probabilities of all the received symbols, I will definitely get 1, right? Because P of y1 is the probability of receiving y1, P of y2 is the probability of receiving y2, right? So probability of receiving y1 plus probability of receiving y2 plus probability of receiving y3 up to plus probability of receiving yn, right? We are sure to know that at least one of the symbols will be received, right? It's a sure event. So therefore it is equal to 1. Or in other words, sigma j is equal to 1 to n, P of yj is equal to 1, right? So now compare these two equations. Here it is k is equal to 1 to m, right? And here it is j is equal to 1 to n. I'm using different variable over here, right? J is equal to 1 to n, P of yj is equal to 1. Okay, so because of these two equations are now being satisfied, we can define the entropy of the transmitter x and the entropy of the receiver y as h of x and h of y respectively, where h of x is the entropy of this P of x. So h of x is equal to sigma k is equal to 1 to m p of xk log 1 by p of xk. This is the entropy of the source or entropy of the transmitter. And likewise, the entropy of the receiver, right? So in the receiver also, this probability is satisfied. Therefore, we can find the entropy of this, right? Which means h of y is equal to sigma j is equal to 1 to n p of yj log 1 by p of yj, right? And these two equations, h of x and h of y, these two entropies are called as the marginal entropies. Here, both h of x and h of y are known as marginal entropies. Okay, so this is the first type of entropies you have studied, h of x and h of y. This is the entropy of the transmitter, this is the entropy of the receiver. And here sigma k is equal to 1 to m p of xk log 1 by p of xk, whereas here it is j is equal to 1 to n p of yj log of 1 by p of yj, where m is the number of transmitted symbols and j is the number of received symbols. Okay. Now next what I'm going to do is let p of x1 y1, okay, joint probability, this is p of x1 comma y1 be the probability that x1 is transmitted and y1 is received. That means both the condition must be happening, both the events must happen, that is x1 must be transmitted and y1 is received. Okay, likewise let p of x1 y2 be the probability that x1 is transmitted and y2 is received. Let p of x1 y3 be the probability that x1 is transmitted and y3 is received. And likewise, if I go for every value of y, right, at the end I will get let p of x1 by n, right, since there are total of n received symbols, right, so therefore up to n, so let p of x1 by n be the probability that x1 is transmitted and yn is received. Okay, so this much probability is there when x1 is transmitted and the received symbols are all y, right? And now in the same way, now I'm going to the next value of x, this next symbol, which is x2. And here also I'm saying let p of x2 comma y1 be the probability that x2 is transmitted and y1 is received. Likewise, let p of x2 y2 be the probability that x2 is transmitted and y2 is received. Let p of x2 y3 be the probability that x2 is transmitted and y3 is received. Right? And same way it goes through all values of all values of x and through all the values of y, right? So how many x are there? How many transmitted symbols are there? M transmitted symbols. And how many received symbols are there? N transmitted symbols. For each of these joint probabilities, I'm saying that this corresponding x is transmitted and the corresponding y is received. And the last element is this, right? This is the last element. Since there are only m transmitted symbols and n received symbols, so this is the last element. Let p of xm by n be the probability that xm is transmitted and yn is received. So therefore, I have covered for all values of x and y, right? In that case, since I'm able to define each and every one of these probabilities, I can say with full assurance that I can define a new type of probability, right? P of xy, which is nothing but a matrix. It is a matrix consisting of m rows and n columns. And this matrix is also called as the joint probability matrix. In short form, it is called as JPM. And it is expressed like this. P of xy is equal to, and if you can see here, if you look very carefully, it is a matrix, right? And this matrix, if you simply look at the first row is what I have written: P of x1 y1, P of x1 y2, P of x1 y3, P of x1 yn. And what are those things? That's what I have written over here. P of x1 y1 is the probability that x1 is transmitted and y1 is received. P of x1 y2 is the probability that x1 is transmitted and y2 is received. Like that, the first row contains those elements, right? Now look at the second row. The second row is P of x2 y1, P of x2 y2, P of x2 y3 up to P of x2 yn. Okay, that is the second row. And look at the third row, P of x3 by 1, P of x3 by 2, P of x3 by 3, P of x3 up to P of x3 by n, right? And likewise, if I follow this pattern downwards, okay, if I follow the same pattern for each and every row, at the last row, since there are m transmitted symbols, there will be m rows, right? So the last row will be P of xm by 1. So P of xm by 1, P of xm by 2, P of xm by 3 up to P of xm by n. So like that, there are total of, this matrix consists of total of m rows and n columns, right? This m rows varies due to the values of x, due to the number of the transmitted symbols. That is how the value of the number of rows varies, and the number of columns varies due to the number of the received symbols n. See, so therefore there are m rows and n columns, right? And in this method, if we add each and every element in this matrix, if I add each and every element in the matrix, P of x1 by 1 plus P of x1 by 2 plus P of x1 by 3 up to P of x1 by n plus P of x2 by 1 plus P of x2 by 2 plus P of x2 by 3 plus up to P of x2 by 1 plus P of x3 by 1. Like that, if I add each and every element in this matrix, and finally P of last element will be P of xm by n. If I add all the elements over here, I will get 1. So since I am able to get 1 for this probabilities, for all these probabilities, I'm adding all these probabilities, when I'm going to get 1, which means that I can define my entropy of this probability also. I can define my probability of this, I can define my entropy of this probability also. So because of equation 3 is satisfied, we can define the entropy of the whole communication system, because this represents the list of all the transmitted symbols being transmitted and the list of all the received symbols being received, right? And for every possible combinations, all the possible combinations are listed in this one single matrix, right? So that is why we can define the entropy of the whole communication system as h of x comma y, where h of x comma y is nothing but the entropy of each and every one of these probabilities, or that means double summation, right? For both for the rows as well as for the columns. Sigma k is equal to 1 to m, sigma j is equal to 1 to n, p of xk comma yj log of 1 by p of xk comma yj. This is the equation of the joint entropy h of xy, h of xy. H of xy is known as the joint entropy, right? So far you have learned about the h of x, then you have learned about h of y, now you have learned about h of xy. Joint entropy. This is called as the joint entropy because it represents the joint entropy. It's called as joint entropy because it's consisting of, this is the entropy of the joint probability matrix. That's why this name is called as joint entropy. Okay, and this covers the entire communication system, right? Because it defines the possibility of every transmitted symbols with respect to every received symbols, right? Now what we're going to do is, from this joint probability matrix, there are some set of properties that you can easily understand, right? See, for example, now if you look at this matrix, the beautiful thing about this matrix is that if you add only the first row, just simply look at the first row. What is the first row? It is P of x1 by 1, P of x1 by 2, P of x1 by 3 up to P of x1 by n. So just simply look at the first row, okay, up to P of x1 by n. Okay, so what will happen if I add only the elements of the first row? What will happen? That is, what is P of x1 by 1? Probability that x1 is transmitted and y1 is received. What is P of x1 by 2? Probability that x1 is transmitted and y2 is received. What is P of x1 by 3? Probability that x1 is transmitted and y3 is received, and up to P of x1 by n. So if I add the elements of all these, what you see here in the first row, what will I get? That is probability that x1 is transmitted and y1 is received plus probability that x1 is transmitted and y2 is received, plus probability that x1 is transmitted and y3 is received, plus, and it goes on, right, up to probability that x1 is transmitted and yn is received. So if I add, so by common sense, right, just by common sense, if I add the probabilities of all these elements, I will get nothing but the probability of x1 itself. I will get nothing but the probability of transmitting x1 itself, right? Because all the received symbols are being covered. Anyone, we are sure that x1 is, this means that adding all the elements of the first row actually means that surely x1 is transmitted and one of the received symbols is received. So which is nothing but the probability that x1 is transmitted. So in that case, if we add all the elements in the first row, we get p of x1 y1. Just simply look at the equation. P of x1 y1 plus p of x1 y2 plus p of x1 y3 plus up to p of x1 yn is nothing but equal to p of x1, because we are sure that any one of these received symbols will be surely be received, right? It either be y1 or it will either be y2 or it will either be y3 or it can either be y4 or up to yn. So any one of these received symbols will be received, but we know that x1 is being transmitted. Therefore, if we add all this, then surely it will be the probability of transmitting x1. Same way, applying the same knowledge to other rows also. If we add all the elements in the second row, we get p of x2 y1 plus p of x2 y2 plus p of x2 y3 up to p of x2 yn. That is nothing but p of x2. In other words, if we add the elements of any row, if we add the elements of any row, right, that is what it says here. If we add all the elements in the kth row, right, where k can be a number from 1 to m. So if we add the elements in the kth row, we get p of xk y1 plus p of xk y2 plus p of xk y3 up to p of xk yn is equal to, it's nothing but p of, it's nothing but the probability of that particular transmitted elements row, right? P of xk. In other words, sigma j is equal to 1 to n, right? P of xk comma yj, because all these elements are changed with respect to j, right? All the elements are changing from 1 to n, right? All the elements in the single row, the elements are changed. All the elements, the xk, the transmitted symbol is constant and the received symbol is the one that is being changed, right? So the received symbol varies from 1 to n. So therefore sigma j is equal to 1 to n. P of xk comma yj is nothing but p of xk. Okay, so this is the fourth equation. Okay, but I have already proved that h of x, right? I have already proved that h of x is equal to sigma k is equal to 1 to m p of xk log 1 by p of xk, right? So what I'm going to do is that I'm going to substitute the value of p of xk over here. Okay, I'm going to substitute the value of p of xk over here. So what will I get? Substituting equation 4 in the above equation, we get h of x is equal to sigma k is equal to 1 to m, sigma j is equal to 1 to n, p of xk yj log of 1 by p of xk. This is the other equation of h of x. This is the other equation of h of x. So h of x has two equations, right? One is this equation and the other is this equation. Okay. Now, this is one thing. This is how did you derive this? When you add all the elements in row wise, right? If you add all the elements row wise. Now what will happen if you add all the elements column wise? Just look like that. Now look at what will happen if I add the probability that x1 is transmitted and y1 is received, plus probability that x2 is transmitted and y1 is received, plus probability that x3 is transmitted and y1 is received, and as it goes down, probability that xm is transmitted and y1 is received. So what will happen if I add each and every elements in the first column? What will I get? I will get p of y1, right? Like that. So in the joint probability matrix p of xy, if we add all the elements in the first column, that is P of x1 y1 plus P of x2 y1 plus P of x3 y1 up to P of xm y1, right? Because there are m transmitted symbols, right? So if I add all the elements in the first column, right, in which if adding all the elements in the first column means the received symbol is constant and the transmitted symbol is varying from 1 to m, right? So if I add all these elements, I will get the corresponding probability of that particular column, which is P of, here first column, so it will be P of y1, right? Likewise, if we add all the elements in the second column, we get P of x1 y2 plus P of x2 y2 plus P of x3 y2 plus P of x4 y2 and so forth up to P of xm y2 is equal to nothing but P of y2, right? Because this means that if we add all these probabilities, right, when we add this probability that x1 is transmitted and y2 is received, plus probability that x2 is transmitted and y2 is received, plus probability that x3 is transmitted and y2 is received. So surely one of the x symbols will be transmitted and y2 is definitely received. That's what this means. So if we add all this, we'll definitely get the probability that y2 is received, right? And similarly, so now this is for the first column, second column. So now if I generalize it, if I take any column, let it be j. If I take the jth column, if we add all the elements in the jth column, we get P of x1 yj plus P of x2 yj plus P of x3 yj plus P of xm yj. If we add all of this up to P of xm yj, we'll get P of yj. Or in other words, sigma k is equal to 1 to m. P of xk yj is equal to P of yj, right? Which means that here if we add all the columns, only the transmitted symbols varies from 1 to m, whereas the received symbol is constant, right? The value of j remains constant. It is the value of k that changes. So that's why it is sigma k is equal to 1 to m. P of xk yj is equal to P of yj. But we know that h of y is equal to sigma j is equal to 1 to n P of yj log 1 by P of yj. So what I'm going to do, I'm going to substitute the equation of P of yj. I'm going to substitute the equation of P of yj in this equation. So what will I get? Substituting equation 5 in the above equation, we get h of y is equal to, so if I substitute this equation over here, I will get this equation, that is sigma k is equal to 1 to m, sigma j is equal to 1 to n, P of xk yj log 1 by P of yj. So therefore there are two equations of h of x and now there are two equations of h of y. That's what it means, right? Now I have derived the marginal entropies and joint entropies. Next, I'm going to derive the conditional entropies. Okay, so for that, I'm going to assume that let P of xk bar yj. We know what this bar actually represents. It represents or it expresses a condition, and this is called as the conditional part, right? This is the event and this is the condition. So let P of xk by yj be the probability that xk is transmitted when we know that yj is received. That is the condition. Receiving yj is the condition. That means we know that yj is received. We already know that. So what is the probability that xk is transmitted when we know that yj is received? That is P of xk yj. And we all learned in school that the conditional probability equation is P of A by B is equal to P of AB by P of B. That is the equation we have applied here. P of xk by yj is equal to P of xk yj by P of yj. Alright. Then so here basically what is constant over here in this probability? The condition is the one that is being constant. This is the variable and this condition is the constant. So now what I'm going to do is I'm going to add the values of all values of k, right? I'm going to add for all values of k, that is sigma k is equal to 1 to m. There are totally m transmitted symbols, right? So sigma k is equal to 1 to m. P of xk by yj is equal to, and I'm going to substitute the equation for P of xk by yj as this equation, right? So I'm going to substitute that over here. I will get sigma k is equal to 1 to m P of xk yj by P of yj, right? So here this summation is with respect to k, and then the denominator there is no k, so I can take this denominator outside. So it will become 1 by P of yj into sigma k is equal to 1 to m P of xk comma yj, right? And what is sigma k is equal to 1 to m p of xk comma yj? It is nothing but p of yj, right? It is nothing but p of yj. So I'm going to substitute this equation as p of yj over here. So it will become 1 by p of yj into p of yj, which is equal to 1. Which means that I can find the entropy of this probability. That's what it means. Thus, we define p of x by yj as p of x by yj is the set of p of x1 yj plus p of x2 yj, p of x3 yj up to p of xm yj, where yj can be any element, right? It can be y1, y2, y3 up to yn. That's what it means. So yj can be any element, and for any particular element, we can define its corresponding p of x by yj. So since this is equal to 1, we can find the entropy of this probability, and this entropy is defined as h of x by yj. Okay, look at the letters very carefully. It is capital letter X by small letter yj, because this represents a condition of a single received symbol, yj. The name of the symbol is yj. It can be y1 or y3 or y5 or y7 or anything, right? So this entropy is defined as sigma k is equal to 1 to m p of xk by yj log of 1 by p of xk by yj, right? And this entropy is defined only for a single element yj, where j is, it can be from any number from 1 to n, where the value of j can be any number from 1 to n, right? Therefore, we define h of x by y, capital letter X by capital letter Y, right, as the average of this entropy. It is the average of this entropy, right? Because this entropy is defined only for a single received symbol yj, right? So now if I want to find the overall entropy, if I want to find the overall average of all the received symbols, so what will I do? I just take the average of this entropy. Therefore, we define h of x by y as the average of h of x by yj for all values of yj. So, in other words, h of x by y is the expectancy of h of x by yj for all j from 1 to n, which means basically it's nothing but simply take its average. So like I said before, how do we take the average? By simply multiplying each and every one of its element with its corresponding probability. So that's why I multiply this h of x by yj. Simply multiply h of x by yj with sigma j is equal to 1 to n p of yj. That's all. So what will I get? So now I'm going to join these two summation together. So it will become sigma k is equal to 1 to m, sigma j is equal to 1 to n, and this p of yj is over here into p of xk by yj log of 1 by p of xk by yj. Okay, but what is p of yj into p of xk by yj? According to this equation, p of xk by yj into p of yj is p of xk yj, joint probability p of xk yj. So that means this can be written as p of xk yj. So which means we will get sigma k is equal to 1 to m, sigma j is equal to 1 to n, p of xk yj log of 1 by p of xk by yj. And this is the equation. This is called as the conditional entropy, or also called as the equivocation. This is the conditional probability, h of x by y. Okay, understand the meaning behind it. It means that the entropy of the source when we know that y is received, when the condition is that y is received. Okay, this is h of x by y. Similarly, the same thing what you have learned so far for this condition problem, the same thing can be applied when you inverse the two parameters, right? That is, let p of yj by xk be the probability that yj is received when we know that xk is transmitted. Okay, so likewise, same case, p of yj by xk, it's a is a conditional probability equation, is equal to p of xk yj by p of xk. Then now if I am, so here this is constant, xk is constant and yj is the event, right? So that means if I want to find the probability for all values of j, right? If I want to find this probabilities of for all values of for all the received symbols, then I will do the summation with respect to j, because xk is constant. So sigma j is equal to 1 to n p of yj by xk is equal to sigma j is equal to 1 to n. I substitute the value of p of yj by xk with this equation, so this will become p of xk by p of xk yj by p of xk, right? So this since this is summation is with respect to j and there is no j in the denominator, so I can take this p of xk denominator outside. So 1 by p of xk into sigma j is equal to 1 to n p of xk yj, right? And what is sigma j is equal to 1 to n p of xk yj? Sigma j is equal to 1 to n. Sigma j is equal to 1 to n p of xk yj is nothing but p of xk, right? If we add all the elements in the row wise, if we add all the elements row wise, so which means this is nothing but p of xk. So this is nothing but 1 by p of xk into p of xk is equal to 1, which means that since this value is equal to 1, which means that I can define the entropy of this, right? That is, we define p of y by xk, right, for a single element. This is for a particular received element per transmitted symbol. Now I'm going to do the same thing for all the received symbols, for that corresponding transmitted symbol. So we define p of y by xk as p of y by xk is a set. It's a set of p of y1 xk, p of y2 xk, p of y3 xk up to p of yn xk. So therefore the entropy of this, since this is all equal to, when you add all this we'll get 1, right? So therefore I can apply my entropy over here. So the entropy of this is defined as h of y by xk and is defined as sigma j is equal to 1 to n, right? Sigma j is equal to 1 to n p of yj by xk log of 1 by p of yj by xk. Then this is for a single element k, right? Single element k, where the value of k can be from 1 to m. It can be x1, it can be x2, it can be x5, it can be any element, right? That's what it means. So for a single element. Now I want to find the value of h of y by x, capital letter Y by capital letter X. Therefore, we define h of y by x as the average of h of y by xk for all values of xk. Right? Because this is for a single element. Now I want to find for all the elements. So what I do to find for all the elements? I just take the average of this. Average with respect to k. Right? Average with respect to xk. So h of y by x is nothing but the expectancy of h of y by xk for all values of k from 1 to m. So therefore, how do I take the average? Like I said before, how do I take the average? By multiplying each and every element with its corresponding probability, which means nothing but simply multiply the sigma k is equal to 1 to m p of xk with this entropy. And that's what we get over here. Okay. So therefore, sigma k is equal to 1 to m p of xk, sigma j is equal to 1 to n p of yj by xk log of 1 by p of yj by xk. Alright. So now what I'm going to do is I'm going to interchange the summation. So this will become p of k is equal to 1 to m, sigma k is equal to 1 to m, sigma j is equal to 1 to n, p of xk into p of yj by xk log of 1 by p of yj by xk. Now what is p of xk into p of yj by xk? It is, what is p of xk? If I bring this p of xk over here, it will become p of xk into p of yj by xk. So what is that? That is nothing but p of xk yj, right? So p of xk yj. So this is nothing but p of xk yj. So this will become sigma k is equal to 1 to m, sigma j is equal to 1 to n, p of xk yj log of 1 by p of yj by xk. Okay, this is the equation. This is h of y by x. And this is also called as the conditional entropy or equivocation. So therefore, there are total of 2 marginal entropies, 1 joint entropy and 2 conditional entropies. Okay. Now let us just do a summary of all the different types of entropy we have learned so far. The first type of entropy you have learned is h of x, right? And what is h of x? H of x is defined as the average information per symbol transmitted by the source, or it's also called as the entropy of the source, or source entropy, or marginal entropy. H of x is the marginal entropy, and there are two equations that define H of x. The first equation is sigma k is equal to 1 to m p of xk log of 1 by p of xk. And the other equation is using the joint probability matrix, right? That is sigma k is equal to 1 to m, sigma j is equal to 1 to n, p of xk yj log of 1 by p of xk. This is the first entropy you have studied in this derivation. The second entropy you have studied is h of y, which is the average information per symbol received by the receiver, or it is also called as the entropy of the receiver or the receiver entropy. And this is also a marginal entropy. This is also called as the marginal entropy. And to define this h of y, there are two equations for that. H of y is equal to j is equal to 1 to n p of yj log of 1 by p of yj. It is also equal to p of k is equal to 1 to m from the joint probability matrix, right? So sigma k is equal to 1 to m, sigma j is equal to 1 to n, p of xk yj log of 1 by p of yj, right? The third entropy you have studied here is the joint entropy, h of x by y, right? Which is the average information per pair of transmitted and received symbols, or it is the entropy of the whole communication system, both the transmitter and the receiver, or it is also called as the joint entropy. And this has only one equation, and that is this equation. That is sigma k is equal to 1 to m, sigma j is equal to 1 to n, p of xk yj log of 1 by p of xk yj. Okay, and the fourth entropy you have studied is the h of x by y, right? Average information of the source when we know the value of y, or average information of the source x when we know that y is received, or average information of the recovery or reconstruction of the transmitted symbols from the received symbols, right? Because this means that we have received, we know what is the value of y, right? We know what is the value of y. So from the value of y, how can I reconstruct x, right? How can I apply some filter or some kind of adaptation or anything, and how do I find the value of x from y? That is the entropy of reconstruction. That is h of x by y, and this is also called as the conditional entropy, and this has only one equation, and this is the only equation you need to remember. H of x by y is equal to sigma k is equal to 1 to m, sigma j is equal to 1 to n, p of xk yj log of 1 by p of xk by yj. And you need to remember that unlike other entropies, this entropy has only one equation, whereas for h of y and for h of x, right, there are two equations. But for h of x by y and for h of y by x, there is only one equation like this. Okay, you really need to look at the pattern of the equation and remember it and memorize it. Okay, the last entropy you have studied is h of y by x, which is the average information of the receiver y when we know the value of x, right? When we know that x is transmitted, or average information of the noise or error in the channel, or noise entropy or error entropy, or this is also called as the conditional entropy. Right? Why it is called as a noise entropy is because in this entropy we know what is the value of x, we know what value is being transmitted, we know the value of x, or we know which symbol is being transmitted. So after knowing which symbol is transmitted, I need to know which symbol I have received. So in that case, by comparing the two symbols, the received symbols and the transmitted symbols, I can estimate the noise of the channel. That is why this is called as the noise entropy, right? And this has only one equation, and this is the equation, that is sigma k is equal to 1 to m, sigma j is equal to 1 to n, p of xk yj log of 1 by p of yj by xk. This is the only equation for conditional entropy. So in total, there are two marginal entropies, one joint entropy, and two conditional entropies. Remember each and every one of these equations, because each and every one of these equations are very important when you're going to do the problems. Okay.